So today we're very happy to have Yuhsin Tsai, that is me, giving a talk, talking about the exotic scattering process in direct detection experiments. So this work is based on the project I'm doing with these gentlemen, David Curtin, Zeph Sargent, and USR. So we have put out one paper to emphasize more on the direct detection consequence when you have some exotic process, it's mainly the 2 to 3 scattering process you can have for direct detection. So that's what we emphasize in the first paper, and we are working on a longer version of the paper to talk more about various kind of experimental constraints on the model that can give you this. So the main point in this talk is to ask these 2 questions about this exotic process. So again, remember, in the usual WIMP-like scattering for direct detection, you have a dark matter bump into a nucleus, and the dark matter go out, and then you measure what's the energy you have for the nucleus. And this is the only way you see the dark matter, is just to measure the energy, the recoil spectrum of this nucleus. Now let's try to think like one extension of this simplest case by assuming there's additional guy that can carry away the energy. Okay. Of course, this guy can be different particles. It can be photon, some standard model particle, or it can just be a standard model singlet, so carry some missing energy away. So this is the case we are going to focus on. So if this phi is a standard model singlet, you don't see it, what would the change be to the recoil spectrum, and how would the effect changes the mass measurement in the usual way you do a direct detection. Okay. So that's the first question we want to ask. And then we also want to know what kind of model can give you such a process. Okay. It's not just as simple as you attach a scalar in some of the mediators. If you want the size of the cross-section to be big enough, it actually sets some constraints on what type of model you can have. If you want this 2 to 3 to happen and have to be big enough to see. Okay. Oh. It's fine. Okay. Sorry, I made some mistakes. Give me a second. I opened the wrong one. Sorry about this.
Misspelled Yuhsin. Misspelled Yuhsin.
Yeah, that's it. No, that's it.
No?
Yeah.
Yuhsin? Oh, it's like,
Yeah.
I've been misspelling.
Now we do.
Okay.
Okay, good. Sorry about this. Okay, I just opened the wrong version. Okay, so there will be a lot of stuff in this talk, like different topics, but so let me just tell you the plan, what the plan is. So first I will try to motivate you. It's interesting to think about this 2 to 3 process, and there's you can use it trying to rethink about how to reconcile different experimental results. And from a model building point of view, which will, which motivates you to look at the model with the case that the mediator carries some dark charge. So we call it the dark mediator, dark matter, which can naturally give you this 2 to 3 process. And then I'm going to show you what's the effect for the direct detection, especially on the mass measurement, and then talk about various kinds of experimental constraints. But I'd like to focus a little bit more on the cooling constraint because it's more different from the usual collider constraints, and a lot of physics is in there. And then we conclude. Okay. So first, let's see how are we doing now for different kinds of dark matter experiments. So we have direct detections, and people have been talking a lot about this, and indirect detections, like this is a Fermi plot. If you look at the photon, the gamma ray line, there is a little peak here, correspond to the mass of 130 GeV dark matter. So there's still a discussion about if this can be a real dark matter signal or not. But anyway, the indirect detection can, in principle, gives you what's the dark matter mass is if you see a peak. And there are also collider constraints. It's a very important tool to constrain the dark matter coupling to the standard model particle. Although in most of the colliders, we are interested in now have much higher energy, so usually it's much more difficult to decide what's the mass of the dark matter by using this. But still, it's very important. It tells you how dark matter couples to other particles, and can probably find the mediators in using colliders. So let's focus more on the direct detection today. As you can see, I intentionally pick a plot that includes the irreducible neutrino background. Okay. So these are the neutrinos given by the sun or by the supernova. And this tells you at some point, if you keep excluding the perimeter space, at some point, the interaction between dark matter and the nucleus is so weak, so the number of events were dominated by the background neutrino interacting to nucleus. So at that point, you really need to think about a different way of looking at dark matter, because you just see neutrinos. Okay. So later, when I talk about model building and I say we need a cross-section to be big enough, the minimum requirement is to have it larger than this neutrino background. The other thing I want to remind you is that every time you see this plot, okay, so you see a dark matter quark interaction, a nucleon interaction, and the dark matter mass, always keep in mind there is a lot of assumptions that have come into this plot. Okay. So one thing I want to point out today is all these contours and exclusion bonds are assumed you have a 2-to-2 interaction with the contact operator. So the usual WIMP type of scattering. Right? Because again, in the experiment, what you really see is just a recoil spectrum. You need to know what's the function you want to fit the parameter. And the function we use is by assuming the scattering is a 2-to-2 with the contact operator. That's how we fit all these masses. Okay. So if the process is different from this, you can get a very different result. And just for now, we already see a lot of inconsistencies between different experimental results. Okay? Of course, one way you can take is to say, most of them, just don't know what they are doing. But a more polite way is to say, we need to understand the background for these experiments even more. Okay. Of course, this can be true, and I believe this is probably true at the current stage. But let's say if we keep doing our experiment and we understand what we are doing more and more, at some point, if we believe the thing we actually see are the real dark matter signal, it's still possible that the dark matter signal can show up. Looks like in the like a contradictor way when it shows up. So let's try to think if this actually happens, what does this mean to the actual dark sector we can have? Okay. So these inconsistencies can be a very good probe of the dark sector and the identity of dark matter. So what kind of inconsistencies we have? For example, some experiments claim they see dark matter and some don't, so they put exclusion bonds. Okay. And also, there are some experiments that claim they see dark matter, somehow they get different dark matter mass in the interaction. Or if you combine the indirect and direct detection, for example, if you believe in the 130 GeV gamma line, which is very different, which is much heavier than the dark matter mass you see in the CDMS, for example. It's only 10 GeV dark matter. Okay. So all of this can show up again in the future result. Okay. And there's a lot of discussion have been made by how to kind of reconcile some of these events. For example, people talk about exothermic dark matter, trying to combine the CDMS and the xenon, saying that maybe the dark matter, when dark matter is scattered, it's scattered into a lighter dark matter, so inject energy into the nucleus, so which will make the CDMS result more preferred than the xenon. So that's one way you can do this. Or you can have dark matter couples differently to proton and neutron. Don't ask me why, but let's assume if that happens and it couples with one of them as a negative sign, then you can fit the data by killing the xenon event. And a lot of models that having a non-standard form factors in these low energy experiments that can also help you to connect some events together. Or, of course, you can just say I have more than one dark matter that have different masses, and they show up differently in different experiments. This can also be the reason why you have different masses. Okay. So a lot of this have been discussed, but just want to point out that somehow all of this still assume you have a 2-to-2 scattering, and most of them assume you have a WIMP-like scattering with a contact operator. So since, we have done a lot of works in this, for example, non-standard form factors and all this, there's another natural thing to think about for different scattering process is to think what would happen if the process is not 2-to-2, but actually 2-to-3. Okay. So here I just give you some example that what can this 2-to-3 process possibly do. Okay. We spend a lot of time in thinking many of them at the early stage. Some of them don't seem to work, at least in the simple way, so it requires more thought. But here I still want to share this, so maybe you can think about a better way. But this is a very different approach from all the models I have told you before. So for example, let's say if we have a CDMS and xenon type of inconsistencies, so you see dark matter in the detector, in the smaller detector, but you don't see dark matter in the xenon or LUTs. So let's say maybe in a 2-to-3 process, when this additional guy goes out, you have a displaced decay into a pair of photons. Because this guy is light, so it's very easy to get displaced decay of this guy. So in a larger larger detector like xenon, it will get vetoed every time you have a nuclear recoil together with the photon signal. But for the smaller detector like CDMS, they will keep the dark matter event. So if this works, this can be an explanation why you see dark matter in CDMS but not in xenon. Okay. And another important thing is that if this is true, then having a larger detector will not help you because it just always got excluded when you have photon.
Why do they veto those kinds of events?
Oh, because they, every time you have photon, it's very easy. It's from the gamma ray or some.
So they can't point back to within 10 centimeters?
You mean they?
I thought that this event, the nuclear recoil generates photons, but they can't point it back to within 10 centimeters. Is that the resolution? Because they do know where the event happened. They have a fiducial region, right?
Right. No, I think what they worry is if they have a gamma ray or type of thing, they kick out the electron and then.
Is it multiple scattering?
Yeah, multiple scattering.
You're trying to get rid of multiple scattering.
Right. Yeah. So actually, yeah, I confirmed this with the LUX, local LUX people. I think this is the code they use. Okay. So this can be a nice way of doing things, but unfortunately, when we actually try to write a model, it seems like you need a new physics to come in a very low energy scale in order to have the decay to be short enough. Because the phi here is very light, the energy of the direct detection is of order like 10 keV. So if you want to produce additional light guide, the mass needs to be smaller than 10 keV. Okay, so the the decay length is usually very, very low. So if you write down an F min type coupling, you probably need the cutoff to be of sub GeV. And this, I think, from a model point of view, it's very hard because it tells you you probably need some very light electrically charged guy. So it's not easy. But it's still but it's still a very different way to think about things. Okay, so also, if you have this 2 to 3 scattering, the scattering will correspond differently when you have different nucleus. And also because when we make the plot like a 2 to 2, assume it's a 2 to 2, we use the wrong function to fit the data. So of course, if we just use this, we will, I mean, when we do the experiments in using different detectors, we will thought it's given by different dark matter masses. But it's very possible we just use the wrong function to do the fitting. Okay. And later I'm going to show you that it's true in the 2 to 3 case, it gives a very different mass for different, it gives a different mass for different materials. If you fit the data, you assume it's a 2 to 2. For the indirect detection, you can also do something interesting. For example, let's assume the 130 gamma line is true, but you only see a tangent dark matter at CDMS. Okay, what can happen is that, let's say, if you have a dark matter annihilating to a photon and a dark photon. So you can write this model using an axion-mediated dark matter and assign the anomaly cancellation to make this to be the allowed coupling. So this annihilation will give you the gamma energy as the mass of the dark matter. Okay? But now, if you take this for the direct detection, because this dark photon will carry away recoil energy, so you will underestimate the mass in direct detection. Okay. So if this can happen, you expect to see a much lighter dark matter mass comparing to the true dark matter mass you get from the annihilation.
And why is it lighter? This doesn't quite.
Oh, you mean why does it look lighter?
Why does it look lighter?
Yes, I will talk more about this later. But the big picture is the amount of recoil energy depends on, if it's 2 to 2, it depends on how much energy the dark matter carries. So if it's heavier, it gives you more energy.
Yes.
But now the dark matter is heavy, but part of the energy is supposed to give to the nucleus is carried away by the light particle. And the mass is very sensitive to that. Yeah. There'll be more than this, but I will discuss this later. Okay. So this is also the thing we thought about before, but it turns out it's not easy to get a big enough direct detection cross-section in this process, simply because there are too many derivative couplings in this operator. So derivative couplings gives you external energy, which has a velocity separation. So in the end, there will be too many powers of velocity separation, like v to the 6th for this cross-section, and each v is like 10 to minus 3. So it's an interesting idea. It's just a cross-section doesn't seem to be big enough to work, but we just need to think harder about this. But that's fine. The point I want to point out is just that it's also very interesting to think about this exotic process. It can, in principle, give you a lot of different ways to think about these dark matter experiments. And also from a model building point of view, if you think a slightly more complicated dark sector, okay, such that the mediator also carries a dark charge. So when the mediator couples to the nucleons, it has to couple in pairs. Okay, so you have to come with the two mediators. So we just give a name, it's called the dark mediator, dark matter. Okay, because when you do a dark matter project, one very important thing is to figure out a name for your model, and we call it dark mediator, dark matter. So when you have this, it's natural to have this 2 to 3 scattering to be the dominant one. Right? As long as this coupling is not too big, the 2 to 3 would be more preferred. So this is kind of a model building point of view to think about the 2 to 3 scattering.
So does that mean the way you've drawn it though, you're going to have, I see, so you've drawn arrows there, you're going to have, you're not going to, you might think, you're not going to consider the two chi's are going to have the same mass, so you're going to only consider that case? Of course now you could have, they could be different.
That's right. So in principle you can have different chi's. Yeah, so in the simplest case, we consider that's right. Yeah. So
okay,
that's
so
why
they have sort of half the charge of phi.
Right.
Yeah.
That's right. Mm-hmm. Okay. Of course, this is not the only way to get 2 to 3. So there are other possibilities. For example, you can have the scalar another scalar just in the dark sector. But the problem of having this is you will need the quarks to couple to a light scalar. Is not preferred. And of course, you can make the scalar to be heavy, but then the dark matter the interaction cross-section would be too low again. Because remember, once you start to think about 2 to 3, you already get a phase-space suppression from having additional particle in the beginning. Okay, so you want to make this part as big as possible. And same thing happens for the loop-induced process, so you have a loop suppression. And also, as I said, if you can have models with derivative couplings, like to photon or the charge radius for the scalar, and all of this will be much more suppressed because of the velocity suppression. So in the end, it turns out the dark mediator, dark matter thing I have in the previous slides seems to be the easiest way you can make it work and have a big enough cross-section. Okay, so let's focus on this case here. So here, let me give you a simple model that can generate such a process. Let's have another vectorized heavy quarks that can run inside here. Okay? And then let's assume these scalars now don't carry any standard model charge, but they only carry some dark charge. So dark charge will flow like this and then goes away. So you also need this scalar here. There are different ways you can stabilize the dark matter. You can either have the Z3 symmetry, so this gives you this coupling chi phi if you have a Z3 symmetry, so the phi is a complex scalar. Or you can have a Z4 symmetry, so phi can be a real particle. So it's like one for the phase is like pi over 2, and pi. So it's like a Z4 symmetry. So you can write a model for this. It's not a problem. And the most important couplings we are going to consider later when we talk about the experimental constraints is this dimension 5 operator between a pair of quarks and 2 phis. And because it's dimension 5, the size of the coupling can be pretty large. So we need to think about all kinds of constraints. So this is a lambda. And also you have a coupling between the scalar to the dark matter. Okay, so this is y chi. In the simplest case, let's just assume the phi 1 and phi 2 are the same. Okay, so, but in principle, they can be different and have different couplings.
So you're not going to care about naturalness, like scalars.
That's right. So, yeah. So there will be a lot of tunings in this model for first. First, I'm not going to tell you why are these scalars like. Okay, so probably a more model building is necessary. We thought about having a phi as like a pseudo-non-Gaussian boson, but again, every time you have that, you have derivative couplings. So the cross section will be small.
How light is it going to be eventually, your phis?
So like 10 keV or even lighter. Right, it depends on if you wanted to have a further decay or not, but at least lighter than 10 keV. And there will be a tuning on the Recoil coupling, of course, because if the two phis are the same, you can close the loop, it contributes to the Recoil coupling, so it gives you some tuning. But here, let me just assume I don't know that. Okay, and also to simplify the discussion, I'm now going to have some non-trivial flavor structure in this coupling, but in principle you can. So let's take this model and first assume it passes all the experimental constraints. I'm going to talk about this later, but let's assume it for now. Let's look at what's the consequence you will have for direct detection. Okay. So it turns out in the end, when you try to measure the mass at direct detections, you will underestimate the mass of these dark matters. Okay, so we'll have a pseudo-light dark matter from this 2 to 3 scattering. But first, let me tell you how did we do our own direct detection experiments. So we are using a silicon detector like you can buy in the store. It's the CPU. So at least we are improved a lot by at least you can reproduce whatever result I tell you here. Okay, so we simulate the low energy scattering using MadGraph 5. And to make sure we are doing a reasonable thing, we contacted the MadGraph people and to confirm it can be done with MadGraph. And we also cross-check the result with analytical 2 to 2 results, and it all agreed very well. And also we check some kinematic edges in the 2 to 3 scattering, and it all agrees pretty well. So we believe MadGraph 5 can do a right thing for this low energy scattering. So to simulate the actual data, you run this tree-level process between a dark matter and nucleus and emit a phi, and then you multiply that by the nuclear form factor. So because it's scalar coupling, it gives you a big enhancement for the form factor, and then you convolute the results with your velocity distribution and the Helm form factor when you start to think about nucleus. Okay. So in the 2 to 2 case, if you combine everything, it gives you like a lot of factors you need to include, but you can get the actual number. And also the efficiencies and the energy threshold in experiments. So you can do all of this. But before getting the full result of the data, let's try to understand what's the difference between the 2 to 3 and the 2 to 2 process. Okay? So before convoluting all these form factors and the efficiencies. Okay. So for the 2 to 2 process with the contact operator, this is a textbook calculation. The Recoil energy spectrum is flat. Okay, it's totally flat. But you have a maximum Recoil energy is given by the relation between the dark matter and the mass of the nucleus. Okay. So this is the low energy experiment. So it's really like the collision problem between two masses. Okay. However, now if you have additional particle carries away the energy, okay, so you no longer have this flat recoil spectrum. So the spectrum will just falls down when the energy goes away from the singlet. And also, if you think about the model I talked about before, the dark mediator model, if the mediator is light, you will also have different kind of spectrum. So one thing is, comparing to the usual 2-to-2 case, actually in the 2-to-2 case, in the end, when you combine the form factor, it also gives you a folding spectrum. Okay? Because when the recoil energy becomes high, the scatter begins to see the nucleus, but not the whole nucleus. So you don't have the enhancement from atomic number. So it drops down in the end. But for the 2-to-3 process, you already have this folding spectrum, even before you include the form factors. So this, once you have 2-to-3, it will fall faster than the 2-to-2. But of course, it's reasonable because some guy carries away the energy. And this will change the mass measurement you will have. Okay. So let's try to understand the recoil spectrum even more. And there is a way you can relate the 2-to-3 with a contact or with the light mediator process. It's just the only difference comes from you have additional light mediator here. And so that's why when you take the ratio between the two plots, it gives you a 1/ER squared in the final results. Okay. So this Mn times ER, you need to think about this in non-relativistic way. It gives you some like a 3 momentum of the nucleus. So you begin, of course, it's reasonable you have a light mediator, so it's suppressed by some momentum. But if you think this a little bit more, you might wonder why is this just the momentum of the nucleus? Because in principle, it should be the momentum of both the nucleus and the light scalar. Right? So why is it just mainly the nucleus? And this is in fact, it's a very simple property when you have a non-relativistic scatter. Okay? Because when the velocity is very low, when you kicker the kinetic energy, it's always much smaller than the 3 momentum.
So can you go back? Sorry, I sort of asked this before,
Yes.
but you have this contact term and then what you call 3-body.
Right.
So I'm a little confused about why they're different, because I thought that in your 3-body thing, you were basically integrating out some heavy vector-like quark. So doesn't that mean that it's really the same as a contact?
Oh, sorry. The vector-like quark is here. It's
Yeah.
between the 2 scalar and this. So that's true. I integrated them out.
Oh, I'm sorry. So it's
Yeah.
I'm sorry, yeah, the difference is just the light T channel or whatever.
Right. So let's say if you make this scalar to be very heavy.
So that gives you that's right, and that gives you an enhancement at low energy transfers.
Right.
Because that thing is light.
Exactly.
Okay, got it. Sorry.
No problem. Okay, so that's for the heavy guys. The kinetic energy is much smaller than the 3 momentum. But for the 5 scalar, because it's very light, it's still relativistic. So its 3 momentum is about the same as the energy. So when you combine this together, you will see that the 3 momentum of the phi will be much smaller than the momentum of the dark matter and the nucleus. So this tells you, when you think about the momentum conservation, okay, the 3 momentum conservation, the phi will not give, can be negligible. Okay, so it doesn't participate. But phi does carry away a sizable amount of energy in the scattering. So that's why when you have a light mediator, which relates to the 3 momentum, and it will only show up for as the momentum of the nucleus, but not the 3 momentum of phi. This is just some simple things to notice in the low energy scattering. So knowing this, you can begin to write down some analytical approximation of this 2-to-3 scattering. Of course, the full result, in principle, you can just integrate the phase space and write down the full result of the thing. But the recoil spectrum can already be very nicely approximated by using these 2 functions of the recoil energy. I don't want to, okay, let me, okay, so of course for the cross-sectional, when you have this contact operator, it doesn't really depend on the recoil energy for the amplitude. So the non-trivial recoil spectrum is totally given by the space-space integral when you have additional particle goes out. And then you can write down a very nice approximation for this spectrum. And you go from the contact to the light mediator case, we just divide that by the light mediator. And then there is a maximum recoil energy you can get, which is the same as the 2 to 2 case. Okay, because in the extreme case, when all the energies is carried away by the nucleus, then it looks like a 2 to 2 case for the energy conservation. So you can get the maximum recoil energy. So even though it just looks like drops down, but there's really like a h here, a very little h here. It's given by the same form, shows up the same form as the 2 to 2 case. So you basically, you can very well approximate all the results by the same function. Okay. You get a little bit deviation when you scale to a very heavy, when you scale to a very heavy nucleus, but the shape is almost the same and the deviation is tiny. Okay. So you can use the same function to fit everything. And the goal for this is just to understand how does the recoil spectrum depends on these parameters. So it turns out the spectrum, in the end, you have a non-trivial shape just because of phase integral, the phi carries away energy. And for different cases, you can just have different, take care of what's the maximum recoil energy you can have in different cases, then you can have the approximation right. So it only depends on, for different materials, it only shows up for this ER max in this approximation. So one thing I want to point out is that the dark matter mass shows up in this reduced mass form. Okay. So it's the same as 2 to 2. Okay, so I spent some time in talking about this more detailed thing, but now let's try to see what the mass would look like if you really have a 2 to 3 data, but you fit it using a 2 to 2, because you don't know. So in the beginning, you fit it using 2 to 2. So for the spectrum, before you put the form factor and the efficiencies, the 2 to 3 already have a folding spectrum, but 2 to 2 is basically flat and have a maximal ER. When you combine everything together, so here we take the CDMS silicon experiment and put velocity distribution, the form factor, and efficiencies, everything. These are the spectrums you will have for a dark mediator, dark matter model, so which is the solid histograms here, and also for the standard WIMP case, which is the dashed line here. So the different colors here means different mass of the dark matter. Okay. So taking this as example, okay. So in a dark mediator, dark matter, you see this green histogram, and it's given by a dark matter carrying 50 GeV mass. But for the WIMP process, this blue curve is only given by the dark matter carrying a 10 GeV dark matter mass. And remember, in these direct detection experiments, it's not easy to get a lot of scattering events. Okay? So it's not, even though there's a little bit small difference between the shape, but you can basically think there's no way you can distinguish that unless you have a huge amount of data. So for a very long time, we will think this thing is just given by a 10 GeV dark matter, so which would be much lighter. And moreover, again, I remind you that the dark matter mass shows up in the reduced mass. Okay, so one property of the reduced mass is that if the dark matter is much heavier than the nucleus, this reduced mass will only it's really just a nucleus mass. It's insensitive to a dark matter mass. So even though, in principle, if it's the WIMP case, you have a 10 GeV dark matter scatter at the silicon, so the mass is 28 for the silicon, it should be very sensitive to the dark matter mass. Okay. But since the actual dark matter mass is much heavier than what you think, so you really lose the sensitivity of trying to identify the mass, but you don't know in the beginning. Okay. So that's why when you can do a map that for a given 2 to 3 dark matter, so assuming this is the actual dark matter mass you can have, what's the mass you will see if you just assume a 2 to 2 case and in the detection for different experiments. Okay. So as you can see, let's see for the CDMS, you think the dark matter is like 15 GeV, but the true mass can extend all the way from like 20 to 100.
How different is this phenomenology from if I assume that you have inelastic scattering to a heavier final state dark matter? Is that, I forget what that one is called.
Oh, that one is different
dark
because
matter, whatever it's called.
Yeah, so if you have the IDM case, it's still flat, but you will the required the minimum velocity you will have becomes larger. So the shape of the spectrum is still half, but you need large enough energy in order to have the scattering to happen.
Right.
So the shape will not change. Will not change much.
But I thought that, since some of the energy is going into just making the final state, you will also get a more, won't you also get a softer recoil spectrum?
Yes, but in terms of the shape, because it's like a constant value, right? Yeah. So it sets a bounce as a constant value, so it doesn't change the shape of the spectrum. But the cross-section will be smaller when you do the velocity interval.
Yeah.
That's right.
And you could also probably get, at least if you do an infinite number of experiments, but if you could get something like this or not? Would you also be able to fake, would you also get a fake, in one experiment, would you fake a lighter dark matter particle mass, or would there be some additional handle on that?
That's true. There will be, there will be some dependent, non-trivial dependent in the nucleus mass you use. That's right. But it comes in what's the minimum velocity you need for the scattering to happen. And that's true.
And at the end of the day, all you measure is the recoil spectrum, right?
It's a sum of them.
Right,
yeah.
So you get a reduced rate because you have to go further out of the velocity distribution, but you would also measure less recoil energy. Mm-hmm. Or no, I'm sorry, you're saying because you have a minimum energy, so I see, because you need a larger minimum energy to scatter, so you're sort of probing the higher the tail of the velocity distribution. So then maybe at a given rate, maybe your spectrum actually looks similar to the elastic case.
Right.
Is that what you're saying?
Right. Okay. So you think you add on top of different cases together with different incoming energy.
So you're really reducing the rate rather than reducing the energy spectrum.
Right. Mm-hmm.
Okay.
Mm-hmm. But one thing you can do is I will mention later is if you don't have a contact operator, you still have 2 to 2, but you have a light mediator. So that will also change the spectrum compared to the contact operator case. So that can already give you some effect on this, just not as dramatic as they think. Okay, so let's say if this really happened, if this is really the case, in the end, a single dark matter experiment can never be good enough to tell you what the dark matter mass is. Okay, you really need different experiments with different range of nucleus in your target. So when I tell my friends, Shanghai at Michigan and Albert that we have a very interesting pseudo-light dark matter model. So I want to call it PLDN, and he thinks this is just means a pretty length dark matter because it's, you really can do much using a single Dirac detection experiments. Okay, so this is doing the same thing, but I try to make the plot that you're probably more familiar with. So I make a plot of the true dark matter mass as a function of the kind of the size of the interacting to nucleus. Okay. Of course, you can rescale this thing in the end. So I just gives you the important power, like coupling over the cutoff scale square. So again, we take the CDMS silicon experiment and ask if this is given by a 2 to 3, what's the range of the true dark matter mass you can have? That gives you the CDMS result that people think they see in the detector. So comparing to the actual thing, when you, not the actual thing, when the case, when you assume it's a 2 to 2 contact operator, the mass range is from like 7 to 15% for the 1 sigma level. But if it's really given by 2 to 3, the mass all the way to 50 Jeff, they can all give you the dark matter mass like this. Okay.
You're marginalizing over. This is in the model with the light mediator, and you're just basically marginalizing over the parameters just to try and fit the data as best you can.
Yes, yeah. So this is saying if we can fit those Recoil energy spectrum, what's the mass and the interaction I would put in.
Okay.
Yeah. Okay. And also one interesting thing is there's a CDMS light experiment that's trying to have a very low energy threshold. Okay, so look at the low recoil energy case, which will be very important for this model because our spectrum is peaked at the low recoil energy region. So CDMS light can put a pretty strong bound on this type of models. Okay, and then of course you can ask if my dark matter is a thermal relic, what's the interaction strength I expect, and here I want to, and this orange curve here is when you compare the 2 to 2 process to the 2 to 3, so which I'm going to tell you now. So in the simplest model, in principle you can also attach the phi to the dark matter. So through a loop level process, you can still have a 2 to 2 process. Okay. And naively, you will think this is small, but it's actually not so small because this is given by a light mediator. So there will be a 1 over momentum transfer. Okay, I made all this too small, and which is a very low energy. Okay, so even though there's loop suppression, in the end, it can still be sizable. Of course, this can be avoided by having different scalars, but even in the simplest cases, when you have a light mediator, it also gives you some similar effect for the mass measurement, because it changes the recoil spectrum from the beginning. Okay? So it also affects the mass measurement a little bit, but just not as much as the 2 to 3 case. Okay, so is there any question? Yeah. Okay,
so you did a Sommerfeld enhancement for either reading that graph?
Yeah, we thought about this, but we think this effect will only be important would be sizable if you think about the annihilation process. Right.
I usually think that Sommerfeld enhancement is doing this kind of T-channel configuration.
No, that's true. That's true. So we estimate it, and it doesn't give the big enhancement for this, or for the annihilation. It can be. Yeah. Okay, so now let's try to think if
I was just going to ask, so if it's Durkheim mass is only coming in through the reduced mass, essentially how far away, how many standard deviations off would you be at an infinitely large Durkheim mass? It seems like you just lose sensitivity to the mass as you go.
Yeah.
So.
That's right. So right. So if the dark matter mass is very heavy, well, of course, first when dark matter mass is heavy, the dark matter density needs to be small. So there will be one effect on the rate you actually see a dark matter. But if you see it, that's true. I mean, there's no change of the spectrum at all. So you cannot distinguish them if they are just very, very heavy compared to a nucleus mass.
I just seem like you went 1 sigma at, say, 50, but I was saying if you go to 2 sigma or 3 sigma, I mean, how far would that extend out? How far is infinity? Did you look at that? Or?
Oh yeah, so the reason why this is cut is because of the strength, I mean, the interaction strength. And if you make the coupling to be very big, so the interaction can happen, it can go very, very far away. There's no way to distinguish that. Okay, so every time you write a model with the light scalar couples pretty strongly to quarks, there's a lot of experimental constraints to worry about. Okay, so first you have a dark matter self-interaction through a light particle, so it constrains the size of the coupling. And if you want dark matter to be a thermal relic, it also tells you what's the size of coupling you need to have. You have additional vectorized quarks, so there's a lot of collider constraints on that. You have the light scalar phi, so from the thermal history, you will worry about the relic density of phi, and worry about the light degree of freedom during the BBN time, and also if the phi will dissociate the helium that you form during BBN. And then you have a light phi, so you worry about the structure formation. And moreover, you have this quarks coupling to scalars, so a lot of cooling constraints you need to think about. And in the bin dump type experiments, you can probably produce this phi because you have a lot of proton in the bins. You can produce phi, and you can probably see it in the detector. And the coupling might induce some meson decay, not the pion decay because pion is a pseudo-scalar, but you can have a decay like a kaons when you have a flavor changing process, and the kaon decay into pi and invisible like its energy. And of course, it can correct some of the coupling, like giving you an invisible Z decay. But this is kind of minor because the scale we are going to talk about is like a 10 TeV scale. Okay. So a lot of constraints, and we think we have looked at all of this. But of course, I'm not going to get into detail of all of this. Just very briefly, for the thermal history, you can have dark matter self-interaction, dark matter annihilation, and you can just check the bonds for this, and they are not very strong. Okay, it's too small. But one thing that you need to worry a bit more is that when you have a light scalar during the BBN time, it contributes to additional light degree of freedom. Okay, so when you have one complex scalar, it gives you the effective degree of freedom comparing to neutrinos is like 0.9, so which is about 2.2 sigma away from the post-Planck result. So there will be some tension to that. But you can fix that by having a Z4 symmetry and having the phi as a real scalar. So you can make the degree of freedom by half. So it will be not a serious problem anymore. Okay. And then we estimate what's the probability of a formed helium-4 during BBM being killed by this light and energetic phi. And in the end, you need the cutoff scale lambda to be larger than 10 keV-ish to avoid the helium have a sizable effect on the helium density. For the structure formation, the thing we have now is basically another light particle that couples very weakly to the matter fields. Okay, so they are really like another species of neutrino, of light neutrino. And people have studied if it's allowed when you have additional light still neutrino in the universe. And the answer is yes, as long as you don't have too many of them. So if you have a degree of freedom as 2, that's okay. And for the collider constraints, you worry about you produce this light heavy quarks at the colliders, or you have some bounds from the monojet searches, and you can do all of this. And it turns out it only requires the lambda to be a few TeV. So there is a bound there, but it's not too bad. For the bin dump experiment, it's an interesting thing to check because you produce huge amount of protons in these bin dump experiments. So a lot of events you can have, but it just turns out it's still hard to produce enough phi in the end. If you want to produce them in the target, when the photon hit the target, you produce phi, and you want the phi to move long enough to hit the detector and see the signal, it's just no hope of doing that using the current data. And also we look at K-on constraints. Compared to the standard model case, as long as the lambda is of 10 TeV scale, you can see the difference compared to the current experimental result. Okay. So probably the more interesting thing and more important thing in this model is a cooling constraint from stars. Because we have a pretty strong coupling between quarks and the light scalars, so in these stars, as long as their temperature is higher than as long as their temperature is higher than the mass of the light scalar, you can produce a lot of them. And if they just move away, leave the star, they will cool down the star. So naively, every time we have a quark couples to a scalar, we expect the bond to be very strong, like the bond for the dark photon or for the axion type of thing. But it turns out when you have a pair of scalars, the bond can be much weaker. Okay, so we try to do our best to estimate the bonds on this, but of course the detailed numerical simulation is always necessary. Okay, but we think we are doing a conservative thing. So we look at the cooling from the supernova, neutron star, white dwarf, and the sun, and the heat flow inside the sun. And to consider these coolings, the important thing is what's the rate you can produce these scalars, and how far will these scalars move inside the star, and what's the density of it, and what's the time that the scalar can leave the sun, and all of the things. You can do some approximation of this. So we try to do some study of these various channels for the interaction to the matter and for the production, and we do estimation of this. So first, for the supernova cooling, is the one with the highest energy, but it's the one that it can be ruled out. Can be ignored most easily, because if your coupling to the quarks is too strong, they will get trapped inside the supernova. So even if you produce a bunch of them, there's no way they can escape, or they will escape much slower than neutrinos. So it doesn't give you a sizable effect for the supernova cooling. Okay.
Sorry.
Okay, sorry.
So you're saying that they interact even stronger than neutrinos?
That's right.
That energy. What is the energy, by the way? What's the temperature?
Yeah, so it's like 1 to 10 MeV.
MeV.
Right.
And at those temperatures, for the lambdas, there is some larger range of lambdas, right? Isn't there some range of lambdas that's excluded by this?
That's right. So, okay, that's right. So if the lambda is like 1000 TeV, okay, then it can compensate this T square over MW square.
For
That's
the
right.
lambdas that you care about, it's...
Right. Because if it's really
stronger
10,000, you don't see the detection, anyway, because it's below the neutrino backbone.
Okay.
That's right. Yeah, so when I say no significant constraints for the interaction we're interested in. For the neutron star, so first, we haven't really, human beings still don't understand the inner core of the neutron star very well. Okay, there's a lot of models people propose, and you can do all kinds of numerical study. So we just take a conservative estimation of saying, okay, this is the we use the density of the matter and the temperature of the inner core, and just say it produces the phis, and the phi will leave the neutron star and cool it down, and we compare this cooling to the neutrino cooling. So there are two ways the neutron star can cool down, and the more important one is the so-called fast neutrino cooling. It happens in the inner core of the neutron star. It's studied like 20 years ago by some strong Russian people, but we compare with that, and we need the lambda to be larger than 20 TeV for things to work. Okay. So
do you really know, do you even know, is it believed that you even know the temperature of the inner core? I thought there's all this uncertainty about the equation of state. Doesn't that affect the temperature?
Yeah, so the temperature we got is just the temperature people use. So that's true. So
there's some consensus and there's some...
Right.
This presumably has a lot of uncertainty, right? Should I take this with a...
yeah, there's uncertainty. But somehow they're still pretty confident. So the reason why they spend here is uncertainty from the temperature and also the density.
Actually, does your production, I guess I was assuming sort of in my question that your cooling process, the elementary process, does it scale with a different power of the temperature than the rate for neutrinos?
Yes.
So you really do need to know the temperature. Otherwise, you could try to just do some scaling argument, right?
That's right.
So you really need to know the temperature.
Yeah. So this is the bond, the shape of the bond we have, but this is so it's different. Yeah. So in order to have the emission rate to be lower than most of the temperature of the neutron star we see, we need this lambda. However, this estimation, and also the same as the white dwarf, because of time, because it's the same thing, so let's just say this in the white dwarf case. So you can do the same thing for white dwarf, and comparing to neutron star, white dwarf is much easier than neutron star, because it's just a degenerate material inside, so it's opaque, like transparent to photon, and everywhere inside the core has the same temperature. It's a very nice thermal conductor. And then you have a jacket of the white dwarf. It's a non-degenerate particle. That's when the temperature begins to change. So a naive estimation of the production and when the phi carries away the energy, assuming the energy is the temperature of the core temperature, then we'll need the lambda to be larger than 100 TeV. So it's a very strong constraint. However, we are still looking at this, and now we believe it's over conservative because when we did this before, we forgot there is the jacket of the white dwarf. So when phi carries a high energy as the temperature of the core, when it hits the jacket, the scattering length is pretty short, so the phi will have been thermal contact with the jacket and have a much lower energy when it actually leaves the crust of the white dwarf. So the bond can actually be much lower than this. We believe it can be an order of like 10 TeV.
So the naive bound was that they would carry away enough energy to shorten the lifetime of the white dwarf. Is that right?
That's right.
So I guess this, when you're at the edge of the new bound, including the jacket, you may be changing the structure of the white dwarf. The real bound will be that you don't change the structure of the white dwarf too much, like raise the surface temperature or something? Or?
Yeah, that's right. So that's also a concern we need to, yeah. So right.
Because this thing is always being bombarded, right, by these escaping particles that will presumably heat up the star, and they'll radiate away.
Yeah. But actually, the number of phis we can actually produce is not, more than the number of photons you will get. But the thing we think we made it wrong is, so the reason why white dwarf is not cool as much as the case without the jacket is because the jacket will block the photon. So it doesn't just go out instantly.
Right.
But for this number, we haven't included this effect.
And there's a similar thing for neutron stars. You're saying the outside of the neutron star.
Right, there is a temperature profile of the neutron star, ghost star. Okay. For the heat flow of the sun, is not the cooling is not very important because you don't produce much phi. But the problem is if you have too much phi left inside the sun, it can change the structure of the sun because it will participate the heat flow inside the sun. And the people believe they know the structure pretty well. So we need to make sure it doesn't change the structure. And in the end, you compare the heat flow to the photon, it's not a big change. So again, for the sun, it's okay. Okay, so actually I want to conclude.
Sorry, can you just remind me roughly, if I remember right, there were bounds that you believe are around in the 10 TeV range. Mm-hmm. So where is that in the direct detection plot? Where is 10 TeV roughly?
Yes, 10 TeV is very high. Yeah, so you're totally right. I should show that plot again.
But eventually you'd like to see all these.
Right.
Okay, I didn't remember. Oh, 10 TeV is well.
Yeah, 10 TeV. So even 100 TeV is okay. Of course, this also depends on what's the size of white kite you want. Yeah. So if white kite is 0.1, the 10 TeV is already like here.
Yeah. Okay.
Right. So let me conclude directly. Yes. So the point of this talk is to remind you that it's also fun to think about different exotic direct detections because they can have effect in the understanding of this data. And also when you have a mediator carries dark charge, it's a pretty natural thing to think about this 2 to 3 scattering, and which can affect the mass measurements and give you some like dramatic effect when you try to fit the data. Okay, so, thanks.
So I mean, have people not, this kind of thing has not been, just phenomenologically, if you have something, some, quark or QCD operator going into 2 light scalars, just take that part of it. And you have very, very light scalars, like you have KUV sort of masses. Mm-hmm. This is not, the constraints on that sort of thing have not already been worked out.
You mean from what?
Well, just from all these things that you're doing, the beam dump experiments, astrophysics, and so on.
No,
You couldn't find
actually,
anywhere
the thing
where
is-
people have considered that already?
no. Yeah, so we really do a literature study, and yeah, in the beginning we thought this kind of thing must have been discussed before, instead of bonds. But there's only bonds for a pair of quarks and a single scalar, but no pair of scalars. For some reason, I don't know. Yeah. So studying these bonds by itself is already an interesting thing to do.
Any other question? Let's thank Yuhsin again.